Hey everyone, today we'll be going over LeetCode problem 931, minimum falling path sum. In this problem, we are given an n times n matrix of integers, and what we want to do is return the minimum sum of any falling path through the matrix. Now a falling path is a path which starts from a cell in the top row and ends at the last row of the matrix. However, when going down, we can either go diagonally to the left, straight down, or diagonally to the right. Any other ways down are not accepted. For example, one possible path from the top to the bottom would be to start from the 2, go to the 5 by going diagonally right, and then go to the 7 by going diagonally left. You cannot, however, go from this 6 to this 9, as none of the mentioned movements allow this direction. We have here this example with this matrix, and we see that our output is 13. This is because we can take the path starting from the 1, then going to the 5 and ending at 7, which gives a sum of 13. And we can also take the path going from 1 to 4 to 8, and this also gives 13. Now the brute force for this problem would be to use recursive decision trees and effort search in order to take into consideration every possible path that we could have at every point in our matrix. So we would have our starting cell, and we know from our starting cell we can either go to the bottom left, straight down, or to the bottom right. And from each one of these cells, we could then go on to the bottom left, straight down, or to the bottom right. And when having all of our solutions, we would then go and find the minimum solution with the minimum sum. Now we know that the depth of this tree would be equal to the number of rows, because we would have to make this decision for each cell for every row. And so because of this, if n is equal to the number of rows, our time complexity would be n times 3 to the n, because at each point we are making 3 decisions to go either to the bottom left, straight down, or to the bottom right. However, if we look at this grid, we see that we are doing repeated work. In fact, 2 possible paths from the beginning to the end would be to go from the 2 to the 5 to the 9, and another path would be to go from the 2 to the 5 to the 8. We could also find a third path when going from the 2 to the 5 to the 7, and we see that all of these paths have the first 2 steps in common when going from the 2 to the 5. Therefore, it is not necessary to actually compute this smaller subproblem 3 times in order to find the solution for the larger subproblem when reaching the last row. We could instead maintain this information using dynamic programming and allow us to reach the solution in a more efficient manner. Therefore, we could use dynamic programming to solve this problem in an O of n squared time complexity. So what we could do is take advantage of our knowledge of the previous subproblems and use dynamic programming and go through every row once, starting from the beginning, and determine the smallest path to reach every cell in a specific row. And I'll show you what I mean by this. So we know that for the first row, our subproblem is already completed for us because there is no path we can take to reach a cell in the first row. We would directly start at these specific cells. However, when starting from the second row, when we look at this 6, we need to determine what is the smallest path we can take in order to reach this 6. Now we know we could reach the 6 from the 2 or from the 1 in the row above. And so the smallest possible path would be to go from the 1 to the 6, and therefore our smallest path sum to the 6 would be 7. So we can go and update this in our matrix. And we're going to save our solutions in this matrix itself so that we don't use extra data structures or extra memory to solve this problem. We then move on to the 5 in the second row, and we check to see what is the smallest path in order to reach the 5. Once again, the smallest path would be from the 1 above, so we update this 5 and it becomes a 6, because 5 plus 1 is equal to 6. Then for the 4, once again, the smallest path would be from the 1, and so we replace the 4 with a 5. We then move on to the third row, and we see what is the smallest path we can take to reach this 7 in the third row. Now, because our second row already computes the subproblem of the minimum paths to reach the second row, we only have to look at the second row in order to determine the results for our third row. We don't look at the first row any longer. So we know that the smallest path to reach the 7 would be from the 6 in the second row, so we can replace 7 with 7 plus 6, or 13. For the 8, again, we would check to see what the smallest path would be, and its smallest path would be coming from the 5 in the second row. So 5 plus 8 is equal to 13, and replace the 8 with 13. For the 9, once again, the smallest path would be from the 5 above, and so we get 5 plus 9, or 14. Lastly, what we would do in our algorithm is go through our last row and return the minimum number, because that would be the minimum falling path from the first row to the last row. So we would return 13, because the minimum result we have found in the last row is 13. And it doesn't really matter from which cell this 13 is coming from. Again, the time complexity for this algorithm is O of n squared, because as we see, we're going through every cell once. And the space complexity is constant, because we're just reusing the grid that was given to us initially. We're going to start off our code by creating variables to initialize the amount of rows and columns we have in our matrix. Now we know that actually this is a n by n matrix, so we actually have the same amount of rows and columns, but I'm going to create separate variables just to keep the code cleaner. Then we wanted to iterate through our grid. And we said that we can start our iteration starting from the row at index 1, because the row at index 0 is already completed for our subproblems. For the columns, instead, we have to go through every column. Now what we want to do is go and find the top left, the top, and the top right cells for every specific cell in a row. For example, for this 6 in the second row in our example, we know that we could come to it from the top, meaning from the 2, from the top right, meaning from the 1, or from the top left, which in this case, however, would be out of bounds. So we need to take out of bounds situations into consideration. So what we can say is that if the column is not the column at index 0, then we can make top left equal to the cell which comes above and to the left. Else, what we want to do is make this value a value which represents out of bounds, because we're at the first column and cannot come from the left. So we can make this equal to float of infinity, so that it's such a great value that it would never be considered our minimum. Then we can find our top cell as the one that comes from the row above, but the same column. And then we have to find our top right cell. So what we can write is that if we are not in our last column, so not columns minus 1, then top right is going to be equal to the cell which comes above, but to the right. And if we are in the last column, then again top right is going to be taken as float of infinity, because it would be out of bounds. Then we want to update this specific cell, and we're going to update it by adding its current value to the minimum value of the 3 cells we found between top left, top right, and top. So we're going to find the minimum between these 3. And go and add that to the cell's current value. Once we're done with the for loops, we have completed our dynamic programming problem, and we could just simply return the minimum value in the last row of our matrix. Let's make sure this runs. And we see that it works efficiently. Thank you so much for watching this video. If you enjoyed it, please like it and subscribe to my channel. I'll see you on the next one.